Hey everyone, welcome to our last workshop of the week for the StarkNet Hackathon. We're joined by Ben from StarkWare. He's going to be teaching you about bridging on StarkNet. As always, please can we have more than a handful of people with their cameras on? It makes such a difference, especially just it's really nice seeing everyone's faces at the end of the day. And hopefully on the virtual world, we can still see each other. Unless you want to be anonymous, then obviously keep it off. We don't want to see you then. But yeah, not much updates from my side. Please keep the questions up. Ben is more than happy for you to just fire the questions during the presentation. He will answer them. If he hasn't got to it, I'll make sure that he gets to it. But yeah, keep the questions high. And enough from me. Ben, over to you. Thanks so much for being here. Really appreciate it.
Cool. Thanks for having me. And nice to see everybody. I'm Ben. I'm from StarkNet, StarkWare, StarkNet. Yeah, I'm a dev advocate. I've been on board for almost a year now. Today we're going to be talking about bridging with StarkNet. Like Jake said, if you have any questions while we're going through this, feel free to ping them out and we can kind of go through a short, concise answer. And then we'll have a Q&A at the end where we can kind of go over longer form answers. But bridging with StarkNet. So to set the table, kind of what the context is for bridging with StarkNet, bridging is a pretty hot topic as of late, probably mostly because of bridge hacks. There's hundreds of millions of dollars. Let me exit my full screen here. One sec. Okay, that's fine. Yeah, so bridges like wormhole, context, hop, cometh, they're popping up left and right. In the current paradigm, a bridge is really made up of some multi-sig that's holding funds that is, doing some mint burn allocation on each side. And what people use it today is for usually bridging assets. So tokens, NFTs from L1 to L1 is usually the paradigm you see nowadays, but more and more you're seeing L1 to L2 with rollups like Arbitrum, like Optimism, and like us. In a modular roll-up world, roll-up environment, these bridges kind of expand the scope and scale of just bridging assets. So some of these concepts like just bridging tokens and NFTs from one chain to one chain, we can kind of expand upon, and we'll get into that today. This gets into it a little bit, but when you're thinking about an L1 to L2 bridge, especially one that employs zero knowledge proofs like we do, you can get into some pretty interesting architectures. We can stop thinking about just bridging assets like tokens and NFTs, and we can start thinking about bridging permissions, computation, instructions. Especially for a hackathon, this is kind of a fun concept to play around with in your head. If we don't have to trust these bridge operators and these multi-sig holders, what kind of fun can we have with bridges? One more thing about this, one of the things that StarkNet lets you do is you can kind of leverage cheap computation at this layer 2 level. So bridging computation really is a fun idea to play with. Basically, can I offload some computation that's prohibitively expensive to do on L1 off to L2 and then get the results of it back on L1. You can start thinking about things like AI on chain, all sorts of fun stuff. I mean, if you're a dev like me that is in it for the tech and it is in it because you like building things, bridges is really a fun thing to play with. Yeah, and so the other thing is really, can we build less bridges? So like I've seen and like you guys have seen, we're talking about, I think we have to be in the billions of dollars of assets that have been kind of sacrificed to these bridge bugs, bridge exploits, bridge hacks. And a lot of that has to do with these kind of untrustworthy bridge paradigms from L1 to an alternative L1. If we can take some of the trust out of it, we can build less bridges, hopefully. Yep, pass data instead of assets. We talked about that briefly. And then let developers build their own bridges with rich, stateful, expressive layer ones, and so many cool things going on and being developed on L1. We want to be able to give flexibility to developers to kind of bridge, anything that you come up with over to L2 and not have to have some big VC backed bridge do all the footwork. Yeah, so these are kind of some of the high concept ideas for trustless bridges. We're going to get into a little more of the nitty gritty architecture. I hope this doesn't look too intimidating. We're going to walk through it piece by piece. Yeah, so two-way bridges, bridges, you can walk over it both ways. So we're going to start with talking to Ethereum from StarkNet. So here's a little bit of a legend. We'll walk through it piece by piece, but I'll give you a high level overview of where we're going. So when we're bridging L2 to L1, we start with some message that's generated from some client. This is fairly trivial, but it's going to be an invocation transaction that's brought about from typically probably a wallet like Argent. You guys are probably using Argent or Bravos, maybe even Magnity. So yeah, it's just a transaction that starts there and interacts with the StarkNet OS. But then this is where it kind of gets interesting, is in step 2 here. So in step 2, there needs to be a contract on StarkNet that employs a send message to L1 call. And what this is the TX initializes an L2 syscall to send the L1 the message to the L1 contract. We'll go through what that message looks like, but essentially the L2 contract initiates this syscall that lets StarkNet OS know, hey, I have a message that I need to handle. With ZK rollups, some of this this leg here on Stark Prover to the Stark verifier is out of scope. This is the power of a ZK rollup, this Stark Prover to Stark verifier. Follow us for more information. Go look at our docs. It'll be slightly out of scope for today's conversation. Just know that that message does need to be included in a proof of the L2 execution to L1. And then it needs to index that message. So the message that is sent from this contract to StarkNet OS, all of the parameters that make up that message are hashed together, and StarkNet registers the message hash there. Cool. This is another piece of the infrastructure that's important to know, but slightly out of scope for this conversation, is that not only do we need to write a proof of StarkNet's execution from layer 2 to layer 1, we also need to write the state update from layer 2 to layer 1. So this gives us our data availability guarantees. It's what makes us a validity rollup. You can always re-engineer the state of StarkNet just from the data that's been written to these smart contracts on layer 2. And then since we've written the proof, you have guarantees that execution was indeed ran correctly. So just know that the state update is something that we need. But so as far as the messaging, L2 to L1 messaging paradigm, we have 4 here. That message that was indexed by StarkNet OS is then written down to the core contracts on L1. So we have a set of core contracts that really operates the brains of StarkNet on L1. And we log that message that has been initiated up here at the contract level to L1, and then we increment a counter. This is an easy way to think about it. Is you can kind of black box all of this and say, I need to send a message from L2. Okay, I send it from L2 to L1, and it gets incremented, and then someone needs to consume it. So this is where there's a bit of an asynchrony between this and this. A layer 1 contract needs to consume that message from the core contracts for it to finally be registered as a cleared message. And then once it's registered, we decrement the counter. So we've incremented it here. It could sit at 1 forever if there's no L1 contract that comes through and consumes the message. Once it does, we decrement the counter. And then boom, our L2 to L1 messaging bridge is complete. We've sent our message. Let me make sure I didn't miss anything here. L1 recipient contract can consume message in L1 TX. Yep. And then this is the actual code, which we'll look at today. Consume message from L2. Great. So that's high level. We'll kind of use this as a key as we walk through some of the code. Okay, so submit TX, this is just your normal interaction with an Argent wallet. Transactions and invocation transactions have to start somewhere, and they usually start from a wallet. So transaction details, this is a initiation of a withdrawal. So withdrawal is when we have some assets on L2 and we want to take them down to L1. We withdraw them. Cool, pay a fee. And this
one or two questions popping up.
Yeah.
The first one is, what exactly is canonical bridge? Is that the right way of saying it?
Gotcha. Okay, so yeah, what's a canonical bridge? A canonical bridge means that we have some form of history. This increment and decrement that we're talking about, these hashes that are going into message logs from L1 to L2. This is all makes up some version of history of the message passing from L2 to L1. That's what makes it a canonical bridge. If we never updated the state here on 4, this would not be a canonical bridge. There'd be no version of history. Can you give an example of a message, a real use case? Yep, Alex, we'll go through that today. But this is also one. So I want to withdraw some ETH from L2 to L1 would be the example of that. One message consumer should be shown inside Ethereum area, I guess. Yes. So the question is, L1 message consumer should be shown inside the Ethereum area. This whole block is Ethereum L1, and then these denote different contracts on Ethereum L1. So Oleg, that's exactly correct. And then is there any limitation on buffer size of StarkNet core contracts which stores these L2 to L1 messages? That is a good question. I'm not exactly sure what the upper bound would be. We will get into it a little bit today. You can define your own protocol, so you can pass as many pieces, as many felts in the array as you want. That's a good question about the upper bound of the buffer size. I don't know the answer to it, and I'll try to follow up with you afterwards. Buffers don't store only the hash. The buffer don't store only the hash of the message. So when we write a message, we define the message parameters, and maybe this will be a little clear as we move forward. But yeah, you can basically say, I'm going to send an array of five felts down through call data to the L1 message. And in that sense, all of those pieces of data that we send in the message get hashed into the message hash that's indexed. Cool. I'm going to move on a bit. I think some of these answers will be answered. Okay, so 1 here, just initiate the transaction. So 2, we have send message to L1. This is necessary for anytime you're sending a message from L2 to L1, and you can see we even import it from the StarkNet common library here, StarkNet, StarkWare, StarkNet common messages. So yeah, okay, this is a good example of what we've been talking about. We get to define the payload schema that we send in this message. So here we've denoted that the payload size is going to be 3, and then we've allocated to an array 3 different values that for all intents and purposes are arbitrary, except for to this L1 smart contract that knows exactly how to handle that message format, and it lets you basically make your own protocol from L2 to L1. We do have standardized protocols. So, if you're using StarkGate to withdraw and to deposit, we have defined our own that are now standard and audited, but this gives you the ability to kind of handle messages and handle the message format however you wish. Cool. The recipient is an L1, that should say contract, not account. Okay. And that's 2 here, L2 DAP, send message params, and all of that goes into the message hash. Okay. So the message is then registered by StarkNet OS. And when we say registered, it's the hash of all the parameters. There's a brand new block explorer that popped up, written by the guys who do Aspect, the NFT marketplace, and the StarkNet JS library. It's really good. I recommend checking it out. You can get the same information from, either if you're querying the contracts directly, or if you look at Voyager. But you can see the message hash here. It's a hash of all of the parameters that went into that message we defined earlier. So that's what's indexed by StarkNet OS. And 3 here has a couple different parts. That message is sent in the proof, as well as indexed by the OS and getting ready to send to the L1. Yeah, one thing I really like about Stark Scan is they annotate what piece of this process is actually being done in each sequence. So this message has been sent on L2. Since there's no concept of what's going on L1, we know that that's basically 3 here. Everything from 3 has been completed. It's been written in a proof, and it's been indexed and ready to be dispatched to L1. This is a little bit outside of our legend. I just wanted to show you guys, because I think it's interesting, what the call flow looks like for a withdrawal from L2 to L1. I think someone asked for an example. So, the most primitive example of messaging from L2 to L1 is going to be a withdrawal. Someone has bridged over some assets and they want to take them back to L1. So what do we need? So when we initiate a withdrawal, we have a contract address, and we need to send it at the L1 recipient that asset is going to be withdrawn to. And in this situation, it's an ERC20. So we need to send the amount of the ERC20. If it's an NFT, you're probably going to send the token index in that. So we see the call flow here. Another really cool part about StarkScan is it shows you the call flow. In this initiate withdrawal, it's coming from an account contract. So that's why you see the execute entry point here. That account contract calls the initiate withdrawal. And then down here at the bottom of the stack, we see permission burn. And that's where you get the bridge concept. So that token is burned on L2 and minted on L1. Back into our map here. Number 4, message is attached to the state update. So once we've proved it and written to the state update, we can now consume it on L1. We know that there was good execution on L2, and the L1 application that we've written and deployed here on Ethereum knows how to handle the payload format. So its job basically is to go and call that function on StarkNet core contracts and consume the message. Once it's been consumed, StarkNet core contract goes through and says, this message at this message hash has been consumed, decrement the counter by 1. And now everything in the system knows that this message has been passed successfully and cleared on L1. So since it's asynchronous, you can have a L1, or if you don't have an L1 contract here that's consuming, it can just sit here unconsumed for the life of it. You do need this parameter for it to reach its full life cycle. Is there a concept of when to send consume message? So that's a good question. It's just since it's asynchronous, it's whenever it works in your protocol, whenever it works in your contract. There's no issue with that message sitting unconsumed in StarkNet core contract. It's just the state of it if you don't consume it on L1. Cool. Yep. All message data can then be retrieved for later use. Yeah. And then one more thing. So StarkNet state is updated on Ethereum. All sent messages are updated to pending. Again, StarkScan does a good job of explaining what's going on there. So this is from Etherscan. Getting into the weeds, this is what it actually looks like outside of the concept. Log message to L1. This is the state update. So we have a UINT 256, which is the index. what contract sent it on L2, what contract it's meant for, what's the destination contract, and then this being an array of UANT 256s means that we can define any payload we want, which we've already talked about. Cool. Okay, message consumption. This is from the core contract. So this is actually what's going on under the hood when you call consume message from L2 from your L1 contract. So what is it doing? It is making sure that the catch-ack hash is correct. It's obtaining that. It's making sure that the hash is correct. It's emitting an event that's saying, yes, this message has in fact been consumed, and returning the message hash. So this is where we get the counter decrement by 1. The core contracts know that, yes, this has been called. We don't get any replay attacks. And since the caller of this is the from address that we saw earlier, you're not going to, this is kind of where we get the trustlessness. So only the address that this message was meant for is able to consume it. Cool. That's part of the trustlessness we get. Full payload needs to be sent as call data. Yep, then it's decremented by 1. And then, yeah, recipient should be calling StarkNet contract directly, but can trigger arbitrarily. So this goes to Prashant's question. Can be triggered whenever it's feasible or convenient. Okay, does that get us through? We don't have this, I guess this should be 5 here. So message consumed, and that takes us round trip here. Delays. Yeah, so messages are transmitted with proofs. Proofs take a bit of time to generate and propagate to L1. When you are dealing with development on StarkNet, this can be one of the slower things to debug, because you need to, we would say finality is done once your transaction is included in an L2 block. And we have a status for that, for your transaction is as accepted on L2. You guys have probably seen that. That means that your message has been accepted on StarkNet, and there is finality there. But since we are a rollup, we do want to see all of these messages flow to L1, and everything be accepted on L1. So to really debug all of this, it can be a bit of a pain. All of these proof times will speed up as the system moves from alpha to beta. But just for now, message debugging from L2 to L1 can be a bit sticky. So before we talk about the inverse from L1 to L2, does anyone have any other questions from L2 to L1? Will regenesis change anything? That is a great question. For a long time, regenesis was talked about as a reset of state, and if we did continue with that plan of a reset of state, yes, it would have changed quite a bit. The question earlier of what is a canonical bridge, if we did reset the state, we could not make a claim to this being a canonical bridge. The way that we have decided to move forward is with kind of an easier path to regenesis. We're not resetting the state. So a lot of those guarantees will remain the same. And as far as the messaging architecture that we're talking about right now, no, nothing should change from L2 to L1 or L1 to L2. But that's a good question. Cool. So L1 to L2. We'll do the same thing. We'll look at kind of a high level overview of it. And then we'll go piece by piece into what each one of them means and how they look in code. For the most part, this is just an inverse of the way we saw message passing from L2 to L1. So we'll start here at the end of the line. We trigger our application on Ethereum layer 1 to register a message. So instead of consuming a message, we're going to send a message. And we do call, whereas before we called consume message from L2, now we call send message L2 on the core contracts. Similar thing here, it's going to hash the parameters of the message that was sent on L1, and it's going to index that message and increment a counter. And it's going to say, hey, these core contracts have a message that was sent on L1, and incrementing the counter means that it has not been consumed on L2 yet. We'll jump up here now to L2. So before any of this happens, we're expecting that we have a deployed contract on L2 with an L1 handler, and we'll see what that looks like. But in this payload, it's denoting what contract that message is meant for. So that contract should exist up here in your architecture for it to be consumed, and not only exist up here, but also have an L1 handler to handle that function call. So, yep, we jump up here. This contract is deployed, has an L1 handler, and runs some code. So it can, the Cairo code can be, anything that's any arbitrary piece of logic that you understand how to affect after parsing the message out. The rest of this just looks kind of like a Stark proof would function normally. And what I mean by that is your L1 handler is simply Cairo code. And the way StarkNet works in general is once Cairo code is executed, we generate a proof of execution, meaning that we know that that Cairo code was run with a valid state transition. And so everything here, 3 and 3 that we're proving, it's just that we're proving Cairo code, just like we prove any other smart contract on StarkNet. So that's where we get the proof here, handled message attached to the proof. And then the only thing that's different from normal Cairo execution is that StarkNet OS does know, because of this L1 handler, that it was a message. So once it has run its Cairo code execution to completion, it's going to say, okay, I've consumed that message. And in the next state update, it's going to say message consumption is attached to the state update and message is cleared automatically, 5 here. So 1, 2, 3, 4, 5. We'll go through them. What transport medium is used for messages to be exchanged between L1 and L2? Is it an oracle used for that purpose? From L2 to L1, it is call data. It's just written in call data to the smart contracts on L2, on L1, sorry. From L, it's also call data the other way. So we have these core contracts up here on StarkNet. Yeah, there's an inbuilt protocol for message passing. So it's call data this way, and it's also call data this way. So StarkNet knows. Sorry, this is unidirectional. So this arrow is the only thing pointing down. StarkNet only ever needs to query the state of the StarkNet core contract to know what's going on. So if there's another message in this message, the messages that are in this contract storage, StarkNet knows it needs to handle it. L2 listens probably to the events of L1 contract. Yes. So there's events that are spit out for the StarkNet core contract. But yeah, this is unidirectional. So StarkNet only ever needs to query Ethereum L1. So send message to L2 in the same way that we had consume message L2, we have send message L2 on the core contracts. Message is indexed and the counter is incremented. And then we specify the L2 recipient as well as the function selector to call. So even though we have an annotator for L1 handler, we will still have a function selector, which I'll show you in just a sec. This is the code block from the core contracts. So get the nonce, set the UN value for the storage, and then here is your question: emit log message to L2. And so just like Ahmad said, L2 listening probably to events from L1 contract. That is correct on 122. And then we have, we're getting the message hash of all the parameters. Yep. And then L1 to L2 messages. Cool. Do the messages expire after a period of time in the core contract if for some reason they can't be processed or are in limbo? No, they'll never expire. But if once they are cleared from the contract storage. But if a message is sent and it is never cleared, it will still be in that core contracts storage. Okay, so the L1 handler. We talked about that we need in our Cairo code an L1 handler that has the annotation at L1 handler, but you can see the selector actually can be anything that we call. This is from an exercise I'll point you guys to later. So we need to point our L1 message to that selector as well as just the L1 handler. This is interesting. So after 10 block confirmations, your message is confirmed on StarkNet. So yeah, as we listen for the event, we see that a message has been registered, but we don't automatically go through and call that L1 handler on the first block confirmation. We wait for 10 block confirmations and then say, okay, now we can execute the Cairo code at that L1 handler as defined by the message format. Yeah, and then StarkNet initiates the corresponding L2 transaction defined by the contract's L1 handler. I won't go into this too much. We have an exercise for you guys if you're interested in looking at the way these bridges work. I'll point it to you at the end of the workshop here. The important thing to note here is that the function is not named L1 handler. StarkNet OS understands that it needs to call this because it is annotated as an L1 handler with the L1 handler here. Cool. So that's 2. Everything else looks pretty similar to the way we've seen it before. Execution that takes place in this L1 handler is added to the proof and written back to L1. The proof is written back to the L1. So, you can see that from 124 here to 139, arbitrary execution that the developers outlined that needs to happen with that L1 handler has been proved to L1. And then, yep, we include that. We pin that message consumption back into the state update, and then the core contracts on Ethereum layer 1 say, yep, message is cleared, decrement the counter, and we are all set to go. Any questions on the round trip the other way? That jumps us from layer 1 contract registers the message. Layer 2 contract after 10 block confirmations is called L1 handler. The handling of that message is proved, and then the state update writes that the message can be cleared. And we have some good path that everyone can walk through and say, all right, this message has round tripped successfully. Wouldn't that cause a memory leak or something like that? There's no memory leak. You can think of this more as just kind of a key value store, if anything. So let's say, yeah, so is there any cause of a memory leak with the message not being cleared? Yeah, so you can think of this more as a key value store. So, if I have a key value store where the key has a value of 1, and then I'm expecting everything, I would love to see that value decrement back to 0, but it doesn't, nothing's going to happen. The key value store will just have a key value pair that's kind of meaningless at that point. So why is this cool? So, blockchain's talking natively. We have this system of validity proofs that we can leverage, and we can say, we can give mathematical guarantees that all of this execution, as it's defined in the way we talked about today, has been executed successfully and is valid. And now we don't have to have an operator that we trust manage the interplay between the L1 and the other L1, or the L1 and the L2. we have no element of trust in the mechanism, which, at the end of the day is why we're here. It's why we do all this stuff, to limit trust, to not delegate our trust to other parties. Ethereum has certainty of what happened on StarkNet. And Ethereum has mathematical proof that a message was sent. Like we've been talking about, one of the things this opens up for you guys, especially in a hackathon, is designing your own protocol. There's no assumptions made about payload sent, and that's that payload size equals X. It can be anything. Smart contracts on both sides can act upon the data and move assets around. So if you're tired of liquidity waiting in a bridge, design a bridge that has liquidity sitting in Aave. If you're afraid of security, you can implement these protocols around time locking. You can really, design anything the way you want if you haven't seen something in the ecosystem. One thing that is really cool is starting to think about message passing from L2 to L1, not just as assets, but also, using a message for it literally being a message. So you can start sending things like instructions, fully remote controlled accounts. That's a tutorial we're coming out with, but basically an L2 account runs an L1 contract, and makes arbitrary call data. So there, basically is like a zombie account sitting on L1 operated by an L2 contract. I haven't fully worked out the architecture in my head, but there's certain paradigms that you can work with ENS. And basically I can manage my ENS from layer 2 just by message passing from layer 2 to layer 1. Layer 1 liquidity, so you can use layer 1 assets in your applications. Assets, like we've talked about, it's cool. Bridging across modular rollups is cool, but I do think messaging as far as offloading computation and instruction sets is really interesting. But at the end of the day, we're all developers. We all got zany ideas. This kind of opens the door to people implementing whatever they want, whatever wild ideas they have. More resources. So if you want to get a little more in depth in the documentation, I have some resources for you here. I guess I can probably send them out to the chat. This is the exercise I was mentioning. So StarkNet messaging bridge. This has some stubs for you to complete code within and make some tests pass. And then message viewer. So starkscan.co/message logs. Everything in that architecture emits events on both the StarkNet side and the Ethereum side. And so we get really good insight into what's happening in the round trips of all these messages as they go from L2 to L1 and L1 to L2. But if you're operating with just the CLI, it can be a little tiresome to look at. So starkscan.co has kind of packaged all that up in this beautiful UI that shows you exactly what's going on with everything and the state of all your messages. With that, I will round it out. Is there a roadmap for bridging to other L2s? There's not currently a roadmap for bridging to other L2s. If I had to guess, I think that will come from the community. It's an interesting question though. Yeah, you can reach out to me. So you can I'll send out my, this is my Twitter and my Telegram. So yeah, if you have any questions or want help building, yeah, I love all the fresh ideas that are coming out of this landscape. And, like the protocol architectures and the freedom that StarkNet and StarkWare gives the developer to kind of run with things means that, you guys can basically come up with any crazy idea. So I'd love to chat through architectures you guys are coming up with. So feel free to reach out on probably Telegram more than Twitter.
Okay, cool. If there are no more questions, I think we'll call it there. There's normally a question pops in as soon as I say this. So I'll try and take it as long as possible. But Ben, thank you so much. I hope that was super insightful for everyone watching today. Yeah, I'll grab the slides of you of Telegram and then share it on Discord as usual. Yeah, huge thanks to everyone that was here today. But a huge thanks to you, Ben. We really appreciate you being here and kind of growing the ecosystem. It's such a great ecosystem to be a part of, and really is a lovely and friendly ecosystem. I actually still shared something from last night that was pretty spot on. I'm going to maybe drop it in the chat. This kind of sums up the ecosystem, I think, in a good way. But yeah, he's shared that with me after I said thanks, which is quite funny. But yeah, we we really appreciate. It's been a great week of workshops. Thank you. The audience has been amazing. Great engagement, and everyone being here. Thank you so much. So enjoy your weekend, which starts tomorrow. And Ben, thanks so much. I really appreciate you being here.
Thanks, guys. Good luck with the hackathon. See you later.